Welcome, everybody. I'm going to introduce myself briefly, and then we'll start talking about our subject for today. And Nina will as well. So my name is Ryan Michael. I lead the AI innovation team here at DataStax. We work on kind of emerging applications of AI and vector search. And one of the things that we've been working on a lot is GraphRag, which is what we're going to talk about today. So Nina, you want to introduce yourself?
Yeah. Hi, I'm Nina. I'm a staff developer relations engineer at Unstructured. And at Unstructured, we do ETL for LLMs. So we get all of your data from S3 or wherever it is and get it into your Astra database for you.
Perfect. So let me kind of introduce a little bit the problem that we're going to talk about today and kind of the high level of what we're going to be showing you guys. And then Nina will walk you through kind of how Unstructured helps you solve part of it. I'll walk you through how Astra Database and some of the tooling that we built helps you solve the other part of it. We've got a demo for you. We've got questions that we'll take. If you have questions during the process, feel free to ask them. We may defer some of them till the end. Try to use, there's a Q&A thing on the sidebar there. If you use that, it'll be a lot easier for us to keep up with than if you just put them in the chat. Prefer that. This is being recorded, so we'll send out a copy of the recording a couple of hours after it's over. So, don't worry about if you really want to save this for posterity, we'll send that out for you. And we'll be sending out kind of materials and links and things that are related to what we're talking about throughout the process. So let's get started. I'm going to throw some slides up on the screen and kind of talk a little bit about what we're here to talk about, which is GraphRag. So why do we need to talk about graphs in the first place? The kind of high level problem we're trying to solve is that oftentimes AI applications need more than just a vector database. And so what we've been developing on my team in collaboration with Unstructured is a way to provide a kind of hybrid solution that incorporates some of the strengths of vector, some of the strengths of graph information, and gives you metadata filtering with all of this so that you can process your documents to extract all the different kinds of information that they have, not just the kind of vector information. So what are we talking about? What kinds of information are we talking about wanting to capture here? So as an example, if you had built like a question answering bot, you could imagine that the questions that your users ask might be really far away from the answers to those questions in similarity space. And so this is the type of problem that caught people thinking about knowledge graphs as a way of kind of structuring knowledge so that you can have a way of connecting things in different ways. And this is what we're looking at providing as a way of providing this structure between like questions and documents so that you can build a system that ingests your documents and gets both the unstructured content as well as this structured relational information between them. But we've approached this in a slightly different way than traditional knowledge graphs. Traditional knowledge graphs have been around for a long time, but they're not really optimized for these kind of AI-focused RAG type applications. And so we kind of tried to start from scratch and build a simpler solution. And so what we've done is we've taken the approach of just taking your documents, take your vector index, and add a graph layer on top of them. And that will allow you to create connections between documents that didn't exist previously because they're not semantic. They're based on structure. They're based on, being a term that's used in your document, being an entity that's referred to or something like that. And so this will allow you to create these relationships between, for example, past questions that your users have asked and the answers to those questions. And so the next time someone comes and asks the same question, you can do a vector search to find the previous questions that are similar and then follow the graph connections to find the correct answers. And this is a way of capturing different types of similarity rather than just semantic, for example. So there's sort of two parts to being able to implement this type of retrieval. The first part being how you represent and capture this graph information. And then the second part being how you use it. In our kind of data storage system, We represent this graph using documents and metadata associated with them. The metadata allows you to represent things like this document has a URL that links to another one, or this document is from the same section of the document as this other one. And so there's a really rich way of using metadata in this traversal operation, but it doesn't address the question of where does this come from, because we have a lot of different kinds of documents. They have a lot of different kinds of information. And we need to be able to analyze those documents to produce this metadata in the first place. And this is where unstructured comes into the picture. So I'm going to stop sharing this and let Nina walk you through a little bit how unstructured really gives you a rich set of tools to be able to take your documents and construct this different types of information. And I think we're going to go through a demo, or I'll let Nina take it from here. So
thanks, Ryan. Thanks for setting the stage for what we're doing. So I'll start with just a brief introduction to what Unstructured is and what we do. So we are a Series B startup. We have a number of users between our API, open source, and our platform that's pretty brand new. So I'll be doing a demo of it to show everyone how it works. And what we do is we get all of your data ready for RAG or Graph Rag. So we support about 60 plus different file types and get those into your vector database or knowledge graph for you. And so we fit in the tech stack kind of between where all of your natural language data lives in unstructured data formats, between there and your vector storage or knowledge graph. And then the way that we operate is that we might take an input like a PDF, and then let's say you're using our high-res pipeline since you have simpler images and you don't need to throw a VLM at everything. You would get the text extracted with OCR. We could caption the image with a multimodal LLM, and then we would use our proprietary table processing model to extract the table and its structures as text as HTML. And so what's really key for Graph Rag is that we extract a ton of metadata. So we have the file name, when it was modified, the page number, as it's available, we have dozen plus fields, text as HTML, base 64 encoding of images. And the one that's really key for Graph Rag, the way that it's been set up in Astra DB, is the parent ID. So when you have your chunking done by a title, you would have all of that content that's in the narrative text or subtitles below that title linked via that parent ID. And Ryan will walk through more of how he sets it up after we extract that metadata. And so we put this extracted content along with the metadata, and that's the canonical JSON format that we load to a vector database. And so you can also, kind of zooming out a little bit, you can generally think of unstructured as Grand Central Station. So we're kind of taking care of everything in the ETL that you may not even be aware of or think about. So we support 30 plus source connectors. So what about keeping those up to date? I will say that setting up a connector is pretty easy. Maintaining them is very challenging. And same with the destination connectors. We adapt our pipelines to novel data types. We think about prompts and uptime for third-party dependencies. We have a number of chunking strategies that we offer, and we're doing research to add more. And then we, let's see, I can't quite see my slide through this thing. Oh yeah, we preserve the reading order. And we have auto recommenders for an embedding or chunking strategy. And so this is kind of the orchestration that Unstructured Platform offers overall. And now let me share my screen with the platform itself. So this is just the landing page for our platform. There's a lot of stuff to help you get started, like our platform quick start, links to documentation and blog about the platform. And so what we'll do here in this demo is look at how we create connectors and then create our workflow. So I set up the connectors in advance since I didn't want to spend time just like looking through for my credentials for in front of you guys. So the way that you would go to start a connector is you would just click on new connector, and then you would configure the source or destination. And I'll go through what I set up with the file we used for GraphRag. So this is in an S3 bucket. So you just put in the bucket name, your AWS key, and your AWS secret key. And then that's it. That's all you need to get access to your data in S3. And then for our destination, we put in our collection name, Graph Vector Store in this case. We used a default key space. We used a batch size of 20. And then we just put in the API endpoint and the token just from our Astra DB console. And then to create a workflow, you would go to new workflow. And I like to do build it with me. I'll show you how to customize later. And so we've got our Graph Vector Store workflow name. So I just select that source that I just created and my destination. And so you can also do multiple sources and multiple destinations. And then I optimize here for using a VLM. Our Platinum workflow uses a VLM of your choice, and then text embedding 3 large from OpenAI via Azure. I'm not going to reprocess all because that's a neat feature. If you don't select it, every time you add new files, you can just run the workflow and only get the new files added. So now that this workflow is complete, I'm just going to click run, and then that will start running my workflow in my jobs here. So you can see here that it's pending. It takes a little bit of time to run, so I'll just walk through in the previous workflow what actually happens after you kick off a workflow. So you get your information about the job ID and when you started it, and then there's a button to request help if you need any help or have any questions. And you'll have an overview that tracks your progress. And so it goes through every step of the pipeline. So first, it found my one input file in the unstructured graph directory in S3, and it loaded that file, and then it partitioned that file via Claude 3.5 Sonnet, and then processed the file to the chunker. And there we did chunk by title, and we had a lot of other pre-configured chunking options. And then we also processed the file after that through the embedder. And then we see that the file, the one structured file, has landed in our Astra Graph Vector Store. Something I forgot to mention in the workflow editing was that if you just click on the workflow after you set it up with the easy button, you can configure it much more in detail. And so, for example, for the partitioner, you can select a different strategy. So you can also select GPT-4o instead of Claude 3.5 Sonnet. And for GraphRag, something that you want to definitely do is click include original elements. And so in addition to the chunks, you'll have all of the elements and metadata that you'll need to build out your knowledge graph. And then you can just save that. So let's take a look at our job here. That one is in progress. It's in the embedder now, and possibly I messed it up by trying to edit the workflow while I was running it. I actually haven't done that before. So I do want to say it's interesting doing a live demo with just one file kind of downplays the real power of the platform, because this one file takes about 3 minutes to run, and in 30 minutes, you don't get 10 files, you actually get about 1,000. So we have really great scaling for per file that you would see for a larger batch job. So this is what you would run to get your document into Astra DB. And I'll send it back to Ryan to let us know what you do after that.
Yeah, beautiful. So what we just saw there was, being able to take a document, set up a little bit of config, and then you get an enormous amount of really powerful data out of it. The question then is, well, what do you do with this data, right? How can you really leverage that to improve your retrieval? So let me see if this picks up. No, I got to go back to that. All right. So At a very high level, for the graph implementation, what we've done is we've kind of built a new set of traversal operations that incorporate all of that metadata when you're going to find the right documents to create a response in your AI application. And so we started this whole process by looking at, well, what can we do with graphs? And what we found is that existing graph databases were really designed to implement graph queries. They weren't really designed to build AI applications necessarily. And so we said, well, I think there's a simpler solution to this than kind of using a graph database and graph queries and kind of doing all of this complex stuff. And we developed this algorithm that we're kind of looking at a high level here, which is a hybrid of graph retrieval and vector search and graph traversal, basically. And it's optimized specifically for building GenAI applications. So what we're doing here is we're starting with a vector search, and then we're following the graph edges. There's a re-ranking operation that we integrate into this process, and it's an incremental process. So we can kind of explore the graph a little bit at a time, prioritizing the areas that are most similar to our search vector. So it's really kind of a combination of both of them. In order to implement this, you need a really performant vector index, because that's part of how we prioritize the graph traversal. We need really efficient indexing on the edges to be able to have efficient traversal of the graph. And that's where Astra comes in. And we'll look at that a little bit more in a second. Astra is our managed database as a service that gives you, scalable storage, vectors all built in. We just looked at how easy it is to connect that up to the unstructured platform and populate with data. And then we'll see in a second what that data looks like once it's ingested. So using this new type of traversal, what you get is you have several new types of retrieval that you can implement for your AI applications. You still have similarity search, just like you would have in any other vector search. So if you have a query, you can find documents that are most related to that query. You can apply metadata filters, so you can put arbitrary constraints on the documents that you're going to return there. But what we've opened up by adding this graph layer on top of the metadata that Unstructured has extracted are these two new kinds of traversal. The first is what we call traversal search. This is just a fairly simple pull back some vector search results and then expand out from there. It's really good for things like pulling in definitions that are in documents or other things that are kind of a simple contextual retrieval, effectively. The second kind of traversal is an evolution of MMR similarity search, which is a way of balancing getting results that are similar to your query, but not all exactly the same. You can balance diversity in your results with similarity in your results. And MMR, maximum marginal retrieval, I believe, is a way of doing that. And we baked that into the traversal algorithm so that as we're exploring the graph, we're re-ranking all of these results using this MMR algorithm to optimize those two priorities. So let me kind of take a break from the slideshow and share my screen so we can take a look at what this looks like in an actual implementation. Perfect. So the first thing I want to show you is Astra DB. So this is, as we mentioned, the database that DataStax provides. We just saw how easy it is to connect to Unstructured and populate it. This is the result of having run that job. So we'll have, a table that we created. It's a vector table, so it has some configuration around the dimensionality of the vector and the similarity mechanism that we're using. And you can see all the data that we've ingested here. So we've got identifier, we've got the vector that describes it, the kind of unstructured content. There's a couple of these that are different pieces of documents that we've ingested. And then for the graph traversal, this is what's really important, is that we have this metadata field that contains all the information that Unstructured pulled out. Now, in its raw form, we can't traverse it. We have to do a little bit of a conversion operation to be able to use it in our graph. We'll share out this notebook that we're looking at right now. But effectively, we just need to iterate through there and do a little bit of a translation. So we're going to take the metadata that was created by Unstructured, in this case, the element ID and the parent ID, and we're going to create what we call links. So this is the structure of the graph out of those, and then update those documents. We update them in place. We can do this a little bit at a time. We can change how we construct those to incorporate different kinds of metadata. So if we want to change the structure of the graph, we can use different metadata fields. But this tells the traversal algorithm how to use that metadata. I should back up a little bit and just kind of show how we got here in the first place. This is a fairly standard LangChain application. We created some credentials. We instantiated an embedding model here. We're using OpenAI. And then we created a vector store. So this is just the standard Astra vector store, except instead of using Astra vector store, we're using Astra Graph vector store. The interface is otherwise the same, drop-in replacement. And then we're ready to start adding documents to it. In this case, we're going to update the documents in there. So once we've done this translation, once we've taken the documents that Unstructured extracted and formatted them to be ready for graph traversal, we can start to look at what we've generated here. We can see this data in a new way. I've got a little visualization script I'm going to run here that uses some standard tools. And we can start to see the structure of these documents. So this kind of cluster right here is showing you the different sections of the document that we loaded. It's showing you that some sections are densely related to other areas, and some of them are kind of off on their own. There are some paragraphs that are just on their own. And so you can start to understand how this graph exists in your data set. And then from there, we can start to look at how we would actually use this in a retriever. As I said, there's sort of three different ways of accessing this data. The first is the traditional vector search. I'm using traversal search here, but I set the depth to 0 because those are the same. Effectively, because the graph is just an extension of the existing vector search implementation, we can say if a depth of 0 is don't traverse anything, then that's just a vector search. And so what we'll see here is that we get results similar to our query, like we would expect in a standard vector search. But from there, we can now increase that depth. We can say, all right, take those initial results that we found and then expand along the edges that I've defined for them. And so we can see here that we're getting more results, and we're starting to see the structure where if we matched on one chunk of text, now we're starting to pull in other chunks of text that are in the same section, for example, that we extracted with Unstructured, but are still relevant to our query. So we're getting better results by pulling in that information about the structure of the document that we're handling. If we use this MMR traversal operation, the result looks somewhat similar, except we've now applied re-ranking to filter back down to just the top 4 results. But you can see we've got different results. Now we're seeing that there's a connection between the results. And that's because we've identified that this pair of documents that we pulled back are related to each other and related to our query. And therefore, they've kind of outranked some other document that was just kind of on its own. So this is how we can use these new types of retrieval to get more relevant results and more interconnected results, and to use some of the domain knowledge that we have to guide this retrieval process. To use this inside of an application, there's really not much of a change you need to do at all, really. This is a kind of standard LangChain prompt where we have a prompt that we're going to give the model. We're going to create a retriever that pulls back context based on the query that the user uses. We're going to give it one of our new traversal types. And so it just automatically under the hood knows to use the right type of retrieval. And then we can just use it in a chain. You can see here an example. I won't run this right now, but we're able to build these chains using all of the kind of tools that you're comfortable with. We do have, let me show you guys an example of a kind of apples to apples comparison of with and without. So this is a different data set that we put together. This data set is based on a movie review data set. And so we took all of these reviews, we passed them through the same extraction process, we created a graph from them, and now we've got a very simple RAG application where on the one hand, on the right-hand side here, we're seeing the graph implementation. On the left-hand side, we're seeing the regular implementation. So we can ask this a question. I'm going to ask it, movies with a strong female. So what we're going to see here is that this is going to pull back chunks of reviews that match this text. But because on the normal RAG implementation, we're not getting any context around that, we're only getting the specific chunks that match this query. Hopefully this will actually complete. There we go. So you can see here, we're getting results, right? We're getting movies that have strong female leads, but the results are very narrow, right? Like I think you can see that there's better results on this side. And that's because we're able to not only pull in the exact match that we asked for, we're able to get some of the information about it. We're able to use that information about the structure of the review to pull in supporting information that the model can then use to give you a better response. You can really see this if you start putting additional constraints on that. So let's say like that aren't about love. So now what we're going to say is match this, but only show me results that meet this whole kind of constraint here. Oh, you can see this worked. Oftentimes when I've run this query, it's not able to get results back. But again, you can see here, we've got much better results here than we do on this side. We have more examples. They're kind of more appropriate to the response. And that's because we were able to pull in this additional information. So let me stop sharing here. And so I think that's the kind of like the TLDR here, is that by using this new type of retrieval, you can pull in more kinds of information that is present in your kind of source data. And using that information, you can guide your retrieval operation to get the right documents more often and reduce the number of times that your models are generating hallucinations or not able to answer your questions correctly. So I think that's kind of the demo that we've got for you. If we have any questions, I see a couple of questions here. And I think there's, I mentioned that there was a notebook that we just looked at there. That's available. We'll send out a link for that if anyone wants to look at that. There's also a blog post support, around these topics that we'll send out for anyone. And I think Nina's got some links too. But yeah, so there's a question here for Nina. Do unstructured support e-commerce content management systems? Oh, you already answered these questions. Never mind. Mm-hmm. Sorry, I've been talking and not looking at the messages.
Yeah, for anything that we don't currently support, it's great to get feedback about what the needs are in the community so that we can put in feature requests and see if we can get those added for you.
Perfect. So yeah, if we have any other questions, happy to jump into those. Or any other comments. Let's see here. Okay, so let's see. So Griffin Clark's asked, when I have large documents like a 10Q for a public company, how is the graph created / how are relationships defined? So the nice thing about this approach is that you have a lot of flexibility in how you create those connections or how you build the graph. And the 10Q is actually a type of document that we've worked with in the past and that we've actually found Unstructured to be really successful in processing. Part of what Unstructured will allow you to do out of the box is to identify the sort of sections within the document. So there might be an area about disclosures, there might be a section of the document about various things. So that structural information is one source of kind of connections that you can build a graph from. There are others that you could use custom extractions for. So if you wanted to apply like a named entity extraction model to the chunks, that's something that you could use to identify companies that are mentioned in one section of the document and as well as another and connect those together. Or if you wanted to do things like identify locations that are mentioned, other things like that. So part of the library that we've contributed to LangChain, that we worked with LangChain to develop, is a set of out-of-the-box edge extractors that supplement what unstructured provides natively. So if there are special types of data that you want to pull out that aren't available, some of them may be available in the LangChain library that we've been working with. Someone asked about how MMR works. Yeah, so MMR is an algorithm that it's basically a way of combining two ways of ranking documents. So you can imagine if I search for something and then I take that search string and convert that into a vector, I embed that as a vector. One way of finding documents is finding documents that are closest to that vector, where the similarity or the distance between that vector and vector space and all of my documents is the least. But you could imagine if you had a bunch of documents that were very similar, like maybe they just had a couple of characters different, or you accidentally ingested them twice, or they were from like the same author, so they were very similar. Those might form a cluster in vector space. And if that cluster was really close to your search vector, and you asked for, say, 5 documents, you might get all of those 5 documents from that same cluster, and they would all have roughly the same information. What you really want in an ideal world is to find things that are near your vector, but they're different from each other. So they have different information. They're sort of a different point of view on how to answer your question. And so what MMR does is it computes for each of the documents that you've decided you're going to return, how similar are they to each new document that you might want to return? So it kind of keeps a candidate set and then adds documents to that candidate set. And what that does is that it makes sure that you can kind of spread your results set out in vector space around your query instead of having them all clustered in one spot. And it can be really helpful in cases where you want to get a sort of diversity of opinions about the documents that you're returning. In the graph traversal implementation, what we're doing is we're doing the exact same thing, but we're applying that as we explore the graph. So as we find new nodes in the graph, we'll use that same algorithm to decide whether or not that node in the graph should be explored and should be returned as part of the result set. So queries, let's see, how to monitor the queries which doesn't have related data, retrain, add data into this rank. I'm not sure. I may not understand this question from Siva, but I think there are a lot of monitoring mechanisms built into, for example, LangChain has LangSmith, which is a really good monitoring system. I know that Unstructured, the platform, has a lot of really good visibility into what's happening there. I don't know, Nina, if you want to talk about the sort of visibility mechanisms you guys provide.
You mean visibility into the data, or?
Well, no, the processing that's happening in terms of being able to see the jobs that have run, how they, what the steps involved are and whatnot.
Oh, yeah. So you can track all of the steps, and our documentation really details everything about what's happening in each of those steps. So I would say that, and the Q&A chat with the documentation can help you find what you're looking for information on. But yeah, there's definitely good visibility there.
Yeah. There's a question about building the graph is data type specific. So yes, the point of the graph, the goal of the graph is to allow you to take the different types of information and knowledge that you have available and expose them to your application. And so it's really going to depend on what is that kind of information. What are you trying to represent? What is the sort of source of information that you're trying to capture? So sometimes this is going to be a very similar process, right? So we're looking at the structure or the links that are present in the document. The sort of the format of this information oftentimes will be similar, but it's going to depend on what you're trying to represent. If you're trying to represent like how like different terms have different meanings in different documents, that's going to give you one kind of type of graph. If you're trying to represent something like how documents link to each other to kind of explain, how to go deeper into a particular topic. Oftentimes, when people are writing documents, they'll create a hyperlink that says, go read this if you want to know more. And so if you're pulling in those links using the link metadata, that's going to give you a different kind of flavor of graph solution. And it's really going to depend on what you're trying to build. So the data type is always going to kind of be, it's going to always be sort of documents with metadata in terms of what we were trying to transfer into. I may not understand that entirely, but how about on other languages using this approach? Results would not be affected, right? So the kind of primary implementation right now is in LangChain, and that's primarily in Python. So if we're talking about other kind of implementations like the TypeScript LangChain, we don't actually have the traversal implementation in there currently on the traversal side. In terms of being able to process the data, there's a lot of flexibility in terms of how you, like, what types of documents you can deal with, what types of extraction you want to apply to those. So I think that's something that we can do across several different contexts, but the retrieval operation currently is implemented in Python. So. Is this LangFlow completely relying on LangChain or other frameworks when doing multi-agent processes? So right now we've implemented, actually this is a good point. We've implemented the graph kind of search operation in two different environments right now. I had forgotten to mention the second one. The first is LangChain, which is what we've been looking at here, and it was the first implementation. The second is our LangFlow product, which is another kind of data stacks offering, which I didn't get into very deeply, but could be its own kind of live stream. LangFlow is a visual editor for building AI applications. And so you can use these same graph retrieval techniques. You can use the same data extraction process. You can use Astra DB, obviously, as a component in a LangFlow flow. I think they're called flows. And so those are the kind of two platforms that this is currently provided in on the query side. So LangFlow is also Python based, but it's a sort of turnkey. You can build your flows in this graphical editor and then run them, take them to production directly as just like a Docker container or something like that. So it's not as language specific in that case. So. So there's a question about how efficient GraphRag is in terms of tokens compared to normal RAG. So this depends on how you set up your retrieval. In the example that I showed, I think, let me verify this before I go and share my screen on this. Yeah, so let me show you this example that we were just looking at. This URL, by the way, which we can share, let me, well, anyway, this is publicly available, so you can go play with this yourself if you want to try this out. And it shows kind of tokens at the bottom here. And so what we can see is that the token consumption is pretty much equivalent between them. This one has 2,000 input tokens. This has 2,000 input tokens, basically. What we're really trying to do with GraphRag is not necessarily provide more context so much as provide better context. And so there is a cost associated with traversing the graph and finding those documents. There's some vector searches that you need to do, but you have control over how many documents you provide to the model. So it doesn't really have much of an impact on your token budget necessarily. It may involve doing more vector searches than you would do in a naive implementation. And so there's kind of a trade-off there between the cost of doing vector searches, which is generally orders of magnitude less than the cost of doing inference. But that's the kind of the countervailing piece right there. And so that's the kind of the cost trade-off there, is that you're putting more effort into the retrieval operation, but you can potentially provide less context, honestly, at that point, just because if you've got better results, you don't need to provide as many.
I see a question from Shivam. I am working in an organization similar to the FBI. We have thousands of documents, and we are working on creating linkages between different entities and across various documents. How can we achieve this? So in our continued effort in using Astra and Unstructured for GraphRag, we have some upcoming next steps where we're creating a plugin that will also extract entities. I think that will probably be, I don't know, available maybe late Q1 or early Q2, and that will be really push button. I would say in the meantime, Unstructured works with organizations also similar to the FBI and others that have a lot of security concerns. So we have Unstructured Platform available in VPC coming soon. And overall, we've built the platform with security and privacy in mind. And we have a recent blog post I think it's not quite out yet, about our security and our enterprise offerings, but it'll be out very soon. So I would say if you are looking for this kind of near term, then you can connect with us and kind of maybe work with our ProServe team or something. That's kind of the way that we help bridge the gap. So I guess, Shivam, I'll just share my email and I can link you with the right folks at Unstructured if you're interested in doing this more near term.
Yes, and I think entities are a really powerful way of kind of connecting documents together. That there's a lot of interest in that. So let's see, follow up on the MMR thing. So the question here is, I wanted to know how different is the mathematics behind MMR compared to similarity search. So they're very similar, effectively. The only difference between MMR and similarity search is that the MMR computes 2 values, whereas the similarity search just computes the 1. The similarity search computes the similarity metric, so that's like the cosine distance between two vectors. And MMR also computes this diversity metric, which is basically what is the average distance between all of your different vectors. And then there's a weighted sum. So you basically say lambda times 1, and then 1 minus lambda times the other, and then add that together, and that's your new score. And so it's very similar. You can read all about that on I don't know, Wikipedia probably. I don't have a link offhand, but it's a fairly well understood process. Let's see, there's a question here about chunk sizes. And I think this is one of the things that's really interesting. So when you're designing a system to service a graph query, if you're not using this graph technique, if you're just using vector search, your chunk size is really important because you're having to balance 2 kind of competing priorities. One priority is, how do I find documents most effectively? And in that kind of world, what you want is you want your chunks to be pretty small, because you want to have a good match between the documents that you're searching for and the query that you're making. The problem is that the bigger your chunks are, the more kind of extra information you're putting into that embedding. And so the kind of more watered down your similarity becomes. And so for finding information, there's a big premium on using smaller chunks. But once you get the chunks back and you're going to go and use them, having really small chunks kind of shoots you in the foot, because your model doesn't have all the information it needs at that point. The contextual information around the chunk can be really helpful. So there's ways of mitigating this. You can do kind of, overfetch. You can pull the preceding and the following chunks. I think graphs are a sort of generalized solution to this problem, though. They allow you to say this chunk is associated with all the other chunks in the same section. This can be using the metadata that we just saw extracting from Unstructured. You can use a summarization process to create a summary of that section, and then that. You can do parent-child. Basically, all of the different techniques that exist for solving this problem boil down to creating a graph over your documents. And so this is why we found this to be such a useful way of doing that, is that it lets you use small chunks to have kind of good search results, but maintain all all of the context around those chunks. In terms of kind of cost, I think the kind of observation there is that the more chunks you have, the more vectors you're producing, and so the more kind of rows you're putting into the database. I'm guessing that's the cost issue there, and that is a trade-off. That's a balance you'll have to strike between kind of what is the granularity required to solve your problem versus what is the cost there. So I don't know that I have a solution for that. I would say take a look at Astra. We have really competitive pricing. We have really efficient vector indexing. Yeah, I think those are kind of like the trade-offs you need to make there. So
I see a question from YouTube. Does Unstructured allow to connect to e-commerce websites and get all the data from all the pages? So one of the file types that we support is HTML. We have a strategy for that called FAST, which is very inexpensive. As I said before, you don't need to throw a VLM at everything. There's like simple text-based parsing that works really well for HTML that we've really optimized on our side. So I would say if you have those web pages loaded somewhere, then you could just put those in a bucket or something, and then get all of the data extracted into JSON. You probably would need to do some more processing after that, I would guess, to get the information you're looking for, but that would make it more machine readable.
So there's a question about, the question is, as documentation becomes dated, can you speak to the maintenance at the vector level? And I think this is a cross-cutting concern that both Unstructured and Astra have a part in. Do you want to talk, Nina, about kind of how Unstructured handles changing data?
Yeah, so I had mentioned this briefly in my demo where I pointed out the reprocess all button, and I think I just skipped over rerunning workflows as well, but I'll expand on that a bit more. So if you are not reprocessing all the documents in your source, we are tracking if, for example, file names or what has been modified has changed. So you could run the workflow again, and then you would only, let's say you're changing 5% of your documents every day, and they're small changes, we will only reprocess those documents for you. We also are shortly putting out event-based processing, so you could have it triggered by updating your documents, and then it would run just on that document and add it to your vector database or wherever you have downstream. And so these are really important cost-saving measures because, without that kind of detailed tracking, which we do in a very secure way where we have a control plane and a data plane so that we really don't have any access to the data that you have in there, but we're able to track if it's changed and only process that data.
Yeah. And then once you've got it in the database, one of the benefits of the way that the kind of graph is implemented, just using metadata, is that once you've updated that metadata, your graph is updated. There's no additional step that you need to do there. Astra lets you modify vectors in place. And one of the other things that really sets Astra apart from most vector stores is that updates made to the vector index are immediately visible. It's a real-time database. Many vector databases have they collect a bunch of changes, and then there's a kind of an index maintenance process that runs periodically. Astra keeps that up to date in real time. So as soon as you update one of the graph nodes, you change the metadata associated with a document, that is immediately available for query. And because we are kind of doing that traversal lazily, we're using that metadata to identify the graph at query time. You don't even need to go through and update the edges. In a traditional graph database, you would have a separation between nodes and edges. And if your node changes, you might need to go and find all the affected edges and update those. You don't have to do any of that. It's all on the document using the metadata. And so once you've updated the document, your graph is up to date. So I think it's a really important consideration. Updates is an important consideration that people often overlook when they're not in production yet. So it can be something that kicks you in a little bit.
Yeah, a related question from Siva here about a website with lots of articles where on day one we have loaded this XML data into a RAG vector database. After a week, you extract the latest files and load the new file into the vector database. And now you have some duplicate data. How should we handle this? One, I would suggest using unstructured, because we're not just writing to your vector database, we're also reading. And this is, again, only metadata based. We never look at your actual data with the same system that has access to the files. And so there, if we saw that a file had updated, we would actually remove the previous vectors that we had written and write the new ones just on these updated files. Or if you had a set of files that had been written before and you've added new files, we would only add the new ones to your vector database.
So we've got two questions, I think, that are kind of on this topic of duplicate data, which I think is a common problem, especially when you're doing these kind of document ingestions, because you don't entirely know what's in the document. It's easy to ingest the same document twice without really knowing, or to have two versions of the document that are ingested. And there's kind of two ways you can deal with this. One is proactively. You can go through and try to keep your database clean and eliminate like duplicate versions. But the other one is that MMR is actually a really good solution to this problem in many cases. I think that's what MMR was kind of designed for, because what it'll do is it will allow you to, with a kind of a small tweak to the trade-off between similarity and diversity, it'll allow you to basically only take one of those duplicates and ignore all of the rest of them. There's a cost again with this. MMR is similar to MMR also increases the number of results you need to pull back from the vector database, because the vector database is not doing MMR natively. It's a client-side operation. So if you have a bunch of duplicates, they will still show up in the initial database access. They'll show up, but they'll get filtered out as we're applying this MMR algorithm, and they won't show up in your result sets. So that's the benefit to keeping your data clean, is that you won't retrieve them in the first place if you have duplicates. But MMR is really good at basically saying, if I have 5 copies of the same chunk, I'm not going to reuse them. The other thing that I think is really useful in terms of avoiding this kind of like data duplication is keeping a lot of this metadata, like we were talking about, that unstructured provides around, especially around provenance. So like, what URL did this come from? What document is this a part of? And so if you find that you've ingested the same path multiple times, it gives you a handle to be able to go and remove all of the results that share that same path. So but keeping all that metadata around can be really helpful for just doing kind of data cleansing and maintenance in the database. Let's see. Do we have any other questions? Looking for new questions. How does this approach deal with complementary information on the same document? So I'm not sure I may have misunderstood the question a little bit, but I think there's kind of two ways I could approach this question of complementary information. In the one hand, we have the duplication, which we were just talking about. That's kind of within documents or across documents. So that would end up producing roughly the same outcomes. If what we're talking about, though, is like an example that we've used in the past is if you're like scraping a web page that's like a support web page, and there's links between documents, or if you're ingesting Wikipedia, and you want to be able to kind of identify when there's a term in a document that's referring to another document that has more information, sort of like expanded version of that. That's where this can come in and be really useful, because what we can do is we can when we process the document, when unstructured processes that document and converts it into smaller chunks, we can identify the links between those chunks and the other documents, and then that can become one of the edges that we use. And this is something that we've seen to be really powerful, where if we have a chunk of text and it has, links to 5 different documents, and those documents contain the explanations of the terms, by following those links, we get much better, richer understanding of what that first document was referring to. So I think that's another kind of complementary information that you can pull in. Links are a really good way of doing that. Entities are a way that you can do that. You can also just write your own parser. So if you have kind of some specific format that you're dealing with, and you want to identify when something is like a named term, for example, if you have a legal document, oftentimes legal documents will have a kind of very specific format of referring to, see subsection 3 of area 5 or whatever. And so what we've seen is that some customers will write custom parsers to basically extract just that type of a reference to another section or something like that. So I think you have a lot of flexibility on top of the kind of like out of the box metadata that's being extracted in the unstructured platform. You can also do like a secondary process that goes out and pulls out more custom fields. So, all right. Well, I feel like we may be, oh, no, there's some more. All right. Like to digitize a local language translation dictionary. Yeah, so I think these are the types of use cases that are really useful, like dictionaries and glossaries and things like that. So I think being able to identify when a particular term has a meaning that is not what the model assumes it is based on kind of scraping the entire internet is something that you can provide that context using this graph connection. It means that you'll need to kind of like, there's kind of 2 steps to that. The first is processing your dictionary. So taking your dictionary and creating documents to represent each entry, and then linking up from your source content to the elements in the dictionary. And so that's, that's where it gets a little bit harder. LLMs can be really helpful for this actually. I've mostly been describing extractive techniques that are deterministic, right? So I know Unstructured is using some very sophisticated models to kind of deconstruct the model or deconstruct the document. Once you have chunks, you can also pass those through an LLM and ask for things like, are there terms which seem to be used here? Can you extract links to those and reference those back to the dictionary? I don't know if there's more to talk about the kind of model underlying the extraction, Nina, or
yeah, I'll just say that we have a number of different strategies that depending on if it's a local translation dictionary that's been like weathered and then scanned, you can use the VLM pipeline to extract it. Or if it's a simpler, if it's an easier to read file, you could use the high res strategy, and that will just get all of that text extracted for you to then process as you need next.
Perfect. Okay, well, thank you guys all for coming. It's been great questions. This has been a great kind of present conversation. As we said, we're going to pass out, or we're going to send out a recording here, as well as our contact information. So, if you want to follow up, I think I'm certainly available. I would imagine Nina is also available to kind of have follow-up conversations if you have additional questions you'd like to get more details on. And obviously there's going to be a lot of materials that you can go kind of read more about. If you want to understand more about Graph, understand more about how unstructured works, we'll be sending out supporting documentations. We'll send out the examples that we showed, and try to make sure that you get all the information you need. And yeah, so this has been great. Thank you so much for showing up.
Yeah. Thanks everyone for the very lively discussion after our presentations. And I guess we've got a call to action on the screen. Unstructured has our own webinar that we're putting together next week that does a deeper dive into unstructured. If folks have more questions there, that's a great place to join as well.
Perfect. All right. Thank you guys so much.
Thanks everyone.
All right.
Questions. I had a brief moment where